Alright, grade 11 chemistry. We're talking about the big thing today. Today we're talking about converting grams to moles. This is absolutely the most important mathematical skill that you can possibly gain in this course. We're going to be using it constantly in this unit, in the next unit, in the last unit. It just shows up every single time. You're going to use it in grade 12, you're going to use it in university if you do university chemistry. I mean, this is the big one. Like, this is the thing you want to get really good at. And thankfully, we have a lot of practice for you to get really good at it because we use it all the freaking time. So, here's what we're going to talk about today. First, we're going to talk about why. Why do we use the mole? Then we're going to talk about atomic mass, and then we're going to convert between masses and moles. So, that's what we're going to get to, and it's this last piece, converting between masses and moles, that is incredibly, incredibly important. So let's start with that. So first off, why do we use the mole? Why use the mole anyway? What's the point? First off, we don't use the number of particles. That's just dumb. No one's going to go and say, oh, I have 300 septillion water molecules, and I have 200 septillion oxygen molecules, and what's going to happen. Like, no, we use moles. That number is a shortcut for a reason, but it makes identifying reactions a lot easier. And here's kind of a good example of why. Like, why don't we just use grams? We have scales, we can figure out the mass of something in grams. Well, different chemicals have different molar masses. This here are 1 mole quantities. These are 1 mole quantities of different things. This is a mole of sulfur, like the 602 times 10 to the 23 atoms of sulfur. This is 602 times 10 to the 23 atoms of iron. 600 times 10 to the 23 molecules of salt. 600 times 10 to the 23 molecules of potassium dichromate. And 602 times 10 to the 23 molecules of sucrose. And you can see that they have different amounts, different sizes, different masses for the same number of particles. So, the big idea, the really big idea here, and I've got it bold and underlined and everything, when we want to compare the amount of one chemical to the amount of another chemical, we work in moles. Because moles give us number. Remember, it's like a billion or a trillion. It's just a number. So a mole of something is the same as a mole of any other thing. It's just that number, that thing kind of like dozen. And it's important for chemical reactions. So to kind of drive the point home, I came up with the sandwich analogy. By sandwich analogy, let's say you ask me how many sandwiches I can make, and I tell you I have 253 grams of bread, 302 grams of ham, and 178.4 grams of cheese. Well, I mean, that's exact. I gave you a mass. That's fine. I can weigh my bread, ham, and cheese. That's easy. Not useful. Not when we're trying to make a sandwich. Not when we're trying to put these together and make something. Then that something has to have specific ratios. But if I tell you I have 16 slices of bread, 10 slices of ham, and 9 slices of cheese, then you can figure out how many sandwiches I can make. In this case, I can make 8 sandwiches because I have too much ham and too much cheese. Right? The masses don't tell you that, but the quantities do. Hence, we work in moles. We work in moles because the masses can lie, but the moles do not. The moles are just a number. So we're always interested when we want to compare two chemicals, we want to convert between chemicals, we're always going to be interested in converting the mass into the number of moles, or any other thing we can get into a number of moles. A volume into moles, a pressure into moles, various other things. But if we want to take something through a chemical reaction, we have to be using moles. Because it's a number, because it's an amount. Because it's not really a unit at all. So I'm going to pause, and we're going to get to the next thing, and the next thing is the concept of atomic mass. So now we're going to talk about atomic mass. Atomic mass is something that we see on the periodic table, and the description is right there. Atomic mass is the mass of an atom. And the mass on the periodic table is related to the mole. What we see on the periodic table, that mass number, is related to the mole. As I talked about yesterday, the mole concept, or actually I think it was Monday, mole concept is that carbon 12 atoms, we have 12 grams of them, that's 1 mole. And so on the table, we see that the mass of carbon is very close to 12. It's because there's isotopes. There's carbon-13 and carbon-14. It brings the average mass up. 6.02 times 10 to the 23. Hydrogen atoms weigh 1.01 grams. Single hydrogen atoms. They weigh 1.01 grams. What about the gold atoms? Well, in order to figure out how much a mole of gold atoms, so that's the 1 mole of gold atoms weigh, we need to find a periodic table. We need to go to a periodic table. And this is the most official periodic table we can get. It's from the International Union of Pure and Applied Chemistry. They're the people that figure out, all of the nomenclature rules. They tell us all kinds of things. And they've got this official table that they put out. So this is the most recent version of the official table, last updated in 2018. Our question is, how much does a mole of gold atoms weigh? So let's have a look. Gold is here, 196.97. Now there's no unit there. The unit is grams per mole. 1 mole of gold, 6.02 times 10 to the 23 atoms of gold. 6.02 times 10 to the 23 atoms of gold is going to weigh 196.97 grams. This is the most official table, but this isn't the one that I'm going to be using most of the time because in the interests of being official, they have several different masses because people will find different masses for different elements. So instead, what we're going to do, also these are like a lot of decimals, and I don't like that. So I'm going to use this kind of my first periodic table kind of table, literally called the kids' periodic table. And what it's done is it's just the masses. Nothing fancy. And all of the masses are rounded to the 0.01. So whereas the IUPAC table has hydrogen as 1.0078 or 1.0082, my table that I like to use is 1.01. It has the mass as 1.01. So that's what we're going to be using. So in this case, the gold should actually be pretty much the same. Yeah, 196.97. This one has gold as 196.97. So yeah, same thing. So that's atomic masses. The symbol for moles is mole, and the atomic mass on the table is expressed in grams per mole of that atom, of that single atom. So all of these are in grams per mole. Grams per mole, grams per mole, grams per mole. Okay, fair enough. That's for one atom. But we can also figure out the grams per mole of a compound. So that's called molecular mass. This was called atomic mass for the mass of an atom. This is molecular mass, the mass of a molecule, or the mass of a compound. And that mass is equal to the combined mass of its individual atoms. So for example, if I want to find out how much 1 mole of water weighs, I want to figure out the mass of 1 mole of water, I can see that I have two hydrogens, and 1 oxygen. Now I would go to my table, and I would go find hydrogen, it's 1.01, and I would go find oxygen, here it is, 16.00, and I've already written that here, 1.01, 16.00. And then I would put that together. I have two hydrogens, so there's two of them, 1.01 and 1.01. There's 1 oxygen, which is 16 grams per mole. I'll add that together, the 2 hydrogens, the 1 oxygen, I get 18.02 grams per mole. And now I know how much 1 mole of water weighs. And that's how we figure that one out. Every compound has a distinct molecular mass. So water, we just worked out 18.02. Carbon dioxide, 1 carbon and 2 oxygens is 44.01. We can figure that one out by finding carbon, 12.01, and 2 oxygens, 16.00. And so together that'll make 44.01 grams per mole. And this gives us a conversion factor for the chemicals. We convert it from grams to moles and from moles back to grams. So I'm going to go over to some practice problems of determining the atomic mass of a substance. So please join me over on the whiteboard. Alright, so we're ready to roll on some practice problems for molecular mass. We got a periodic table, we got a calculator, that's all we need. I'm just going to start with, let's go with this one, KOH. Let's start with KOH. So KOH, we want to figure out the molecular mass of KOH. Well, we have a K, we have an O, and we have an H. So we have to look it up in our table. We have to find a K, O, and H. So H is 1.01. 1.01 grams per mole. O, when I look on my table here, it's up here, it's 16.00 grams per mole, and K, down in the corner here, there's K, is 39.110 grams per mole. There's just one of each, 1, 2, 3, and so put that together, we're going to end up with 39.1 plus 16 plus, I wrote 6 by accident. So 39.1 plus 16 plus 1.01, I get 56.11 grams per mole. 56.1 grams per mole. So KOH is 56.11 grams per mole. Okay, that's potassium hydroxide. Let's look at the other one here, SO2. All right, SO2. SO2. When we look at it, we have an S, and we have 2 oxygens. So S, I look at my table, I find S. S is right here, 32.07. 07 grams per mole. 2 oxygens, well, 1 oxygen is 16.00 grams per mole, times 2, because there's 2 of them. There's 2 of them, so that's 32.00 grams per mole. Right, 32.00 grams per mole. So to figure out SO2, it's going to be 32.07 grams per mole plus 32.00 grams per mole. And, you know, that's 64.07 grams per mole. 64.07. Yeah, so that's SO2. We're going to go a little bit more difficult now. I'm going to jump down a little bit further. Let's do something like, we'll leave that one alone for now. Let's go for this, CH3COOH. So CH3COOH, right? How many grams per mole is CH3COOH? What is the molar mass? Well, we can figure out how many of each. So we have carbon, we have hydrogen, we have oxygen, we have carbon C, and another carbon C. So we actually have 2 carbons. Hydrogen, we have 3 hydrogens, and then another hydrogen. So there's actually 4 hydrogens, and 2 oxygens, OO, so 2 oxygens. So that's what we're actually going to be calculating. So 2C is 2 times, and then I look at my table, and I find carbon, it's 12.01 grams per mole. Hydrogen, I've got 4 hydrogens, and each one is 1.01 grams per mole. I know that from my table. Right, there it is up here, 1.01. And oxygen, we already saw it just a second ago, it's 16 grams per mole. For some reason, oxygen is like really memorable. So we have to multiply these, 2, 4, and do 2 times 12.01 is 24.02 grams per mole. 4 times 1.01 is 4.04 grams per mole. And 2 times 16 grams per mole is 32.00 grams per mole. We're going to add them all together to figure out what the actual molar mass is. So 24.02 plus 4.04 plus 32.00, and that is 60.06 grams per mole. And that is the molar mass of CH3COOH, so 60.06 grams per mole. 60.06 grams per mole. So that's 3 of them. We're going to do one more, which is going to involve brackets. So we got to watch out for the brackets. Just make sure that we watch out for brackets. So let's we'll go up to this one with our brackets. We have NH4 2 SO4, right? And the brackets NH4 that means essentially that I have NH4. I have 2 of those, right? That's what this is saying. I have 2 NH4s, kind of 2 packs of NH4, like that, and then 1 SO4. So that means in terms of what kind of elements I have 2 nitrogens. I have 2 nitrogens, and in terms of hydrogens, I have 8. I have 4 and then 4, so 4 H4, 2 H4s, 2 H4s. So I actually have 2 nitrogen, I have 8 hydrogen in this molecule because of the 4 times the 2. I only have 1 sulfur because the SO4 is outside the brackets just by itself. And the 4 here is on the oxygen. I have 4 oxygen. And then that's what I'm going to use to calculate my, my molar mass. So we've got to be careful with our brackets when we calculate molar mass. I'm going to just put these over here so that I have more room to work. 8 hydrogen, 1 sulfur, and 4 oxygen. Nitrogen is 2 times whatever nitrogen is. Let's have a look at nitrogen. Nitrogen 4, like here, 14.01 grams per mole. 8 hydrogen. We already saw hydrogen earlier. It was 1.01 grams per mole. We saw sulfur earlier as well. That's 1 times 32.07 grams per mole. And oxygen, we saw it as well, 4 times 16.00 grams per mole. So we multiply the individual ones. 2 times 14.01 is 28.02 grams per mole. 8 times 1.01 is 8.08 grams per mole. 1 times 32.07 is 32.07 grams per mole. And 4 times 16 is 64.00 grams per mole. And we're going to add those together to figure out what our, this was NH4 2 SO4, NH4 2 SO4, ammonium sulfate. That is, we're going to add them together. So let's add them together. We have 28.02 plus 8.08 plus 32.07 plus 64. 132.17 grams per mole. Yeah. So this is something that we really want to get used to doing in order to help support the rest of the course. So yeah, that's a concept. Let's do one last one just to get our brackets straight. We have this one here, gallium sulfite, so Ga2SO3 SO3. So that means we have 2 galliums. We have how many sulfurs? Take a second to think about it. How many sulfurs are in this molecule? If you said 3, you're correct. There are 3 sulfurs because there's 3 sulfites, 3 of these sulfites. You can think of it as sulfite, sulfite, and sulfite. That's the 3 sulfites, right? So 3 sulfurs. And by the same thing, how many oxygens do we have? Take a minute to think about it. We have 9. 3, 3, and 3. We have 9 oxygens on it. So take that away. We need some numbers. We already know sulfur. That was 32.07 grams per mole. We know oxygen. It was 16 grams per mole. Gallium, that's new, so I don't know what gallium is. Let me find gallium on here. Gallium is here. There's gallium. 69.72, so 2 times 69.72 grams per mole. And then we have to put some numbers in, so 2 times 69.72, because I'm lazy, 139.44 grams per mole. 3 times 32.07 is 96.21 grams per mole. And 9 times 16.00 is 144 grams per mole. 144 grams per mole. So that means that this thing, when we want to add it together, is going to be quite large. 144 plus 96.21 plus 139.44 is 379.65 grams per mole. That's a heavy molecule. 1 mole of this stuff is going to weigh almost a pound, which is kind of impressive. So that's, we get 379.65 grams per mole. Yeah. And you know, you can be lazy and you can just search it. So I'll show you kind of here's the lazy way to do it. You open Google. See, now it just asked me to open Google. Never mind. Here. Molar mass of gallium sulfide. Oh, I should have said sulfite. I should have said sulfite. Molar mass of gallium. Ooh. Molar mass of gallium sulfite. Huh. See, it's giving me the wrong one. It gave me gallium sulfide. I know you can't tell, but it gave me the wrong one. Never mind. Sometimes you can Google it. Sometimes you can't. There's a kind of a counter proof of the wrong one. All right, so that's that. We are going to continue on with our thing. We're now going to convert from moles to grams and grams back to moles. So I'm going to pause and get that set up. Okay, so let's say I have this question here. How many molecules of water are in 250 grams of water? Well, we're going to convert 250 grams of water to moles. And once we have it in moles, that's how many molecules are, because moles is just a number, right? It's like billion or trillion or whatever, so that's fine. We can just report our answer in moles. So we're going to jump back over here. I'm going to take away the document capture here. Just give me a sec. That one. So our question is, we have 250 grams of water, grams of H2O, and we want to figure out how many moles of H2O. Well, this sure sounds like a conversion. We're converting grams to moles, and we need to find a conversion factor. Our conversion factor is our molar weight, our molecular weight. We know that H2O has a weight of 18.02 grams per mole. In terms of a conversion factor, that is a fraction. It is 18.02 grams of water per 1 mole of water. Or, equivalently, because we can flip our fractions, it's 1 mole per 18.02 grams. All right, we can flip it. Right? Either way, but that's what grams per mole means. It's a rate. It's those conversion factors we've been talking about. So now we can use that in our conversion. 250 grams of H2O, and we're going to multiply it by a conversion factor, just like we did in the previous video. We need a conversion factor. What goes on the bottom? Well, it's whatever we want to cancel out. We want to cancel out grams. So grams is going to go on the bottom, 18.02 grams, because we want to cancel it, and it's per 1 mole. And so we figure out that we just need to divide by 18.02. So let's do that. Let's do 250 divided by 18.02. and it works out to be 13.87 moles. 13.87 moles of H2O. Right, moles of H2O. Because moles is going to stick around. It's on top. It's our target. It's what we're converting to. So we convert grams to moles. We can use conversion factors to do it, and it's a very helpful way. You never get lost in multiplying or dividing if you just remember that you want to cancel out. You want to cancel out whatever's on the bottom, and you want whatever's on the top to be your target. So we can use the same mathematical trick, the conversion factor, to do grams to moles and moles to grams. So we're going to do a few more practice problems to finish out the lesson, and then we'll do a bunch more in class. So I'm going to set up the practice problems and see you in no time at all. Alright, so we're going to do some basic practice problems here. You'll see just how fast these get eventually. So first question is, how many moles are in 15 grams of lithium? So we have 15 grams of lithium. We want to know how many moles there are, moles of lithium. We need a conversion factor that will be found on our table. Let's figure out the molar mass of lithium. There it is, lithium, 6.94. 6.94 grams per mole. Right, grams per mole. So we want to put one of them on top and one of them on the bottom. Is the 6.94, is it the 6.94 grams on top, or is it the 6.94 grams on the bottom? Well, it's going to be on the bottom because we want to cancel our grams. We want to cancel the grams. 6.94 grams, and that's 1 mole. 1 mole per 6.94 grams. That's what the rate is, right? It's 1 mole for every 6.94 grams. If we have 6.94 grams, we have a mole of it. And so we see that we can divide. We divide by 6.94. Divide by 6.94. It's 2.16 moles. Yeah, 2.16 moles of lithium. And you can prove it by canceling out your units. Grams cancels grams, moles sticks around, so you got 2.16 moles of lithium. That's the first question. Done. So now we've converted a gram, a mass, into a number, and that number we can then use in a reaction. Reactions, using them in reactions is going to be Thursday's video, so that's going to be tomorrow's video for you guys. Hey, there's going the other way. How many grams are in 2.4 moles of sulfur? Well, we have 2.4 moles of sulfur. Okay. We're going to have a conversion factor, some amount of grams of sulfur. And we need a conversion factor. Our conversion factor is going to be the mass of sulfur, whatever the mass of sulfur is. And here on my table it says 32.07. So 32.07 grams per mole is our conversion factor. That's sulfur. Is it on top or on the bottom? What goes on the bottom? Moles has to go on the bottom. So that's per 1 mole. We have 32.07 grams. It's molar mass. And so in this case, we're going to multiply 2.4 times 32.07. So 2.4 times 32.07, 76.97. 76.97 grams of sulfur. And that's our answer. That's how many grams of sulfur are in 2.4 moles of sulfur. One quick thing that you can think here is think of moles as a pack, and this is how much one pack weighs. And you can kind of get this concept of, yeah, I'm going to have more than 32 grams because I have more than 1 mole. Things like that. We're going to keep going. We're going to get down to, maybe there's some more interesting ones. Yeah, how about this one? How many grams are in 0.02 moles of beryllium iodide? Well, in this case, we're going to figure out how much beryllium iodide weighs. I'm going to pause and just write that out for you. So I've written it out. Beryllium iodide, BeI2 up there is 1 beryllium and 2 iodines. So there's my 1 beryllium from the table, 2 iodines also from the table, 9.01, 253.80. I'll add them together. It's 262.81 grams per mole. So we worked that out. We worked out our conversion factor. And now we are going to, we'll just erase that. So that's our beryllium iodide, BeI2. And we want to figure out how many grams are in 0.02 moles. So I have 0.02 moles of the stuff. I want to figure out how many grams of beryllium iodide I have. I'm making a conversion factor, so I want to multiply it by some kind of conversion factor, right? And what goes on the bottom? Well, moles is on top, so I want moles on the bottom. That's per mole. And per mole, I have 262.81 grams. 262.1 grams. 262.81 grams. I'm going to move this over a little bit because it's going to be a little bit long. So 0.02. This tells us that I have to multiply. So 262.81 grams. That tells me that there are 5.25, actually 5.26. 5.26 what? What is my unit here? Well, I had moles and I canceled it with moles. The only thing left is grams. So it's going to be grams of beryllium iodide. So 0.02 moles of it weighs 5.26 grams. So that's the kind of math we're going to be doing during the lesson today. And yeah, thanks for paying attention. And please, please, please work on this worksheet. There's a lot of practice problems. You can see just how many practice problems there are. It's such a fundamental concept that really, really get some practice with it. Thanks a lot, and I'll see you in class.